So again, looking at the original function, our first derivative, our second derivative, you can see that the original function, there's our zeros here, and they relate to the zeros here and here. Okay, and then if you take a look at the max of the zero slope of the derivative function, it relates to the zero on the second derivative. But if we work backwards from the second derivative to the first derivative, well, the max of the first derivative represents this point right here. Now, it was a minimum in the other graph, but basically it's going from this curving up. Okay, so it gets a maximum positive velocity, and then it starts to go, velocity starts to go down, so it starts to level off like this. And that point is called an inflection point. And this is a very useful thing to know then, is that the second derivative, the zero of the second derivative, actually relates to this point here. So this is called an inflection point. Now, just because this is equal to zero doesn't actually mean that there's necessarily an inflection point, but it indicates that that's something that's possible and that's something we can look for. So there, the relationship between the first derivative and in the original graph, well, the zeros of the first derivative match the zero slopes of the original graph. So where this is f prime equals 0 is a max min of f of x. Okay, so when we talk about the parts of the second derivative, so where the second derivative is equal to 0, the second derivative equals 0, we're actually talking about this. There's this potential change of what we're going to call concavity. Okay, and so we're going to say that this relates to, doesn't mean that there is an inflection, but definitely relates to the inflection point on f of x. Okay, so there is this relationship that we can connect the second derivative to something that's going on the original graph. So if we look at this chart here, this chart's very useful. And this is these charts that we want to start drawing when we start looking at functions, because we want to know what the shapes of these functions are. So if my original graph has a max or min, okay, that means that the curvature is like this. That means the first derivative is increasing. So the derivative is going less negative, more positive, more positive, more positive. So the slope of my derivative graph is going to be going up. The change of the change is increasing. So it's becoming more and more positive slope. Okay, so and that indicates a positive second derivative. So when we talk about the slope of the change of the derivative, we're actually talking about the curvature. Okay, how is this original f of x curving? It's what we call concave up. If we take a look at the slope of the derivative, this is a change of the change. Okay, this is a change of the change. It's negative. And the change of change means the velocity is getting more or more negative or less positive. So here we're going from positive, less positive, less positive, less positive, more negative. That means that we have a downward curvature. So not only can we say that the zeros relate to some point, but the positive and negative second derivative actually relate to a curvature. Okay, so if we take a look here, this is a positive first derivative, and notice that the curvature is getting more positive, which means it's what we call concave up. Here it's negative, and the curvature is getting less positive, more negative. Okay, it's becoming more and more negative, so we're going to end up getting a negative curvature, which is we call concave down. Okay, so this is what we mean about the second derivative giving us some indication about the shape of the graph. So here we have the regular slope chart, our relationship between the first derivative and the original graph. Positive first derivative means positive slope. Negative first derivative means negative slope. And you see that same relationship happening between the second and first derivative. But now we can make this connection all the way from the first derivative, the second derivative, back to the original function, and it tells us something about curvature. So there are the web link there is just for practicing matching graphs, so visually being able to match graphs together and getting a sense of how the shapes relate to each other. Okay, so that's important to do, so make sure you get some practice to do that. This last part here is just talking about critical points and inflection points. So we just talked about that inflection point here. So the critical point is when the first derivative is 0. The inflection point is what happens when we change curvature, okay, or we change the change of the change is changing from negative change to a positive change, okay, and this is what we call that inflection point. So what's happening to the slope of the derivative at the critical point? Well, the slope of the derivative at the critical point, f prime equals 0 at the turning point. Okay, so we're giving it lots of different names. So it's a max, min, turning point. Okay, so that's a turning point. Okay, what's happening to the slope and the derivative at the inflection point? Well, at the inflection point, this inflection point here, f double prime is changing from positive, is changing from negative, so we have this negative concavity here. It's becoming less positive, more negative through that whole region, from negative to positive. Let me just write that a little bit nicer. Changing from negative to positive. Okay, so we can see that that curvature is going from what we call concave down to concave up. Okay, well, we're going to investigate this more as we go along, but generally that's something we're going to relate the second derivative to. The second derivative relates to curvature.